17.4 Analysis Model Waves Under Boundary. In this session, we will explore the physics of waves under boundary conditions. We will begin by discussing how these conditions lead to the formation of standing waves and the concept of normal modes. We will then examine how quantization restricts a system to specific allowed frequencies, forming what we call a harmonic series. Finally, we will look at practical applications in musical instruments and the phenomenon of resonance in standing wave systems. Consider a string of a specific length, labeled L, that is held fixed at both ends. When waves travel along this string, they hit these rigid boundaries and reflect back. This creates a continuous superposition where the incident waves and reflected waves combine. Because the ends are fixed, they cannot move, which means the displacement at these points must always be zero. In physics terms, we call these fixed points nodes. The presence of these nodes at the very beginning and the very end of the string is the fundamental boundary condition that governs the wave's behavior. The boundary conditions we just discussed are quite restrictive. They limit the system to specific, discrete patterns of oscillation known as normal modes. This restriction to only certain allowed frequencies is a process called quantization. Quantization is a central feature whenever waves are confined by boundaries. For our string fixed at both ends, the requirement that there must be a node at position 0 and a node at position L effectively dictates which wavelengths can actually exist on the string. The physical requirement for a standing wave is that the nodes must be separated by exactly 1/2 of a wavelength. The first normal mode, which has the longest possible wavelength, occurs when the string length L is equal to 1/2 of the first wavelength. This is called the fundamental, or the first harmonic. As we move to higher modes, the wavelengths become shorter. For the second harmonic, the length L equals the full wavelength. For the third harmonic, the length L is equal to 3/2 of the wavelength. In general, the wavelength for any mode n is equal to 2 times the length L divided by the integer n, where n can be any positive whole number. We can determine the natural frequencies of these modes by using the relationship that frequency equals wave speed divided by wavelength. By substituting the expression for wave speed on a string, which is the square root of the tension T divided by the linear mass density mu, we can find the frequency for any mode, n. The frequency of the nth mode equals n divided by the quantity 2 times the length L, all multiplied by the square root of tension divided by linear mass density. The lowest of these, where n equals 1, is our fundamental frequency. All higher natural frequencies are simply integer multiples of this fundamental value. When the frequencies of a system are integer multiples of the fundamental frequency, they form what we call a harmonic series. The first mode is the first harmonic, the second mode is the second harmonic, and this pattern continues for all positive integers of key call n. This is particularly important in music. When you pluck or bow a string, you are not just hearing one frequency, you are exciting a combination of these harmonics. The specific blend of these different frequencies is what determines the timbre, or the unique sound quality, of the instrument. Let us look at a piano as an example. A middle C string has a fundamental frequency of 262 Hz, while the A string above it vibrates at 440 Hz. If these two strings had the exact same length and density, the tension in the A string would need to be about 2.8, 2 times higher than the C string. This is because the tension ratio is equal to the square of the frequency ratio. However, to prevent the piano frame from collapsing under such massive force, real pianos vary the length and the density of the strings. For instance, if the A string is shortened to 64% of the length of the C string, the required tension ratio drops significantly to only 1.16. In this experimental example, we have a sphere of mass, m, hanging from A string, which creates an initial tension equal to the mass times gravity. When the sphere is hanging in the air, the string is observed vibrating in its second harmonic. If we then submerge the sphere in water, a buoyant force B acts upward. This reduces the tension to a new value: mass times gravity minus the buoyant force. Even though the driving frequency remains constant, the change in tension changes the wave speed, causing the string to shift its vibration pattern to the fifth harmonic. To solve for the radius of the sphere in this problem, we use the ratio of the two different tension states. Since the frequency is constant, the ratio of the frequencies is 1. This allows us to find that the second tension is equal to the square of the ratio of the mode numbers 2 divided by 5 multiplied by the original weight. The buoyant force is then the weight multiplied by the quantity 1 minus the square of that mode ratio. Since the buoyant force also equals the density of water times gravity times the volume of the sphere, we can solve for the radius. For a 2 kilogram mass, the radius of the sphere is approximately 7.37 centimeters. Resonance is a powerful phenomenon that occurs when an external periodic force is applied to a system at a frequency that matches one of its natural frequencies. In this image, we see a vibrating blade driving a string. When the blade's frequency matches a natural frequency of the string, it results in large amplitude standing waves. While a simple system like a pendulum has only one natural frequency, standing wave systems like this string have an entire set of resonance frequencies corresponding to their various normal modes. To summarize, boundary conditions lead to wave quantization and the existence of discrete normal modes. For a string fixed at both ends, the allowed wavelengths are 2 times the length L divided by n. The natural frequencies form a harmonic series, where each frequency is an integer multiple of the fundamental. This fundamental frequency is determined by the length of the string, the tension, and the linear mass density, specifically being 1 divided by 2L times the square root of tension over density. Resonance occurs whenever a driving frequency matches one of these specific natural frequencies. To wrap up, consider these review questions. First, think about a guitar. If you press a fret to shorten the string, how does that affect the fundamental frequency? Use the relationship between length and frequency to explain why. Second, consider the concept of quantization itself. Why is it that a string fixed at both ends exhibits these specific, discrete patterns, while a wave traveling through an infinite medium with no boundaries does not show quantization at all?